when we solve quadratic equations that, we have the quadratic formula that'll solve any quadratic equation, but that it makes, it's messy, right? It's difficult sometimes to do the quadratic formula. Sometimes it can make a mess out of things that could have been done easier. That we have those finer tools like solving by factoring or solving by square roots, but those fine tools only work sometimes. So that's what really type 1 is going to be like, is the finer side of things, that if we can do it this way, we want to because it's faster. Okay. And then type 2 would be kind of the sledgehammer way, like, well, we can't do it the other way, so we're going to log the heck out of it. Okay. So what we want from the problems to make them easy is to have the bases of the powers to be the same. Okay, so you notice on number 1 that there's just, they're all base e. So we can do something kind of more simply that way. And really what this is going to come down to, guys, is that with this, like, if x plus 7 is equal to 2 over 7, what's x equal to? What's x equal to, Grant? Don't make it more difficult than it is. If x plus 7 is equal to 2 over 7, what's x equal to? Correct, not Grant. 2.
I knew that.
Yep. All right, Grant, here it is. If the square root of 15 is equal to the square root of x, what's x equal to?
15.
It's not Grant. All right, Grant, third time's charm. You better be fast this time. If 3 times x to the 2/3 plus 7 is equal to 3 times 42 to the 2/3 plus 7, what's x equal to?
Uh, 42.
There you go. Okay. So there's math behind all of these equations. We could solve all of these equations, but we don't need to, right? I could solve this. I can multiply both sides by 7, but I don't need to. I could square both sides, but I don't need to. I could subtract 7 and then divide by 3 and then raise to the reciprocal power, but I don't need to. Because everything else is the same, I can see that the x and the 42 must also be the same, and so I can just say that. So that's what we're trying to take advantage here, is that if I know that 2 to the 3x plus 7 is equal to 2 to the 10th, then 3x plus 7 must be 10. I can just say that. There's math behind it. There's math behind getting the 2's to go away, but we don't need to worry about it because we can see it in a different way. All right? Does that make sense? How we can just kind of ignore how to get rid of these 2's and we can just approach the problem from a different side. Okay? And so that's what we're looking at here on this first example. We see all those e's down there. Now there's a little bit of simplifying we need to do here because we have too much stuff going on that we needed to kind of do some combining. Oops. All right, and so we look at this and say, well, how do I deal with powers that are multiplying? What happens to these exponents when we multiply powers? Katie, what happens to those exponents when we multiply powers?
The exponents add.
All right, and so we'd end up with e to the 3 plus x, right, equals, and then now over here we have power to a power. So Tiger, what happens to exponents when we have a power times a power to a power?
They multiply, right?
Multiply. So we'd end up with e to the 5 times x, or e to the 5x. Right? Okay. So we have a little bit of simplifying we do. So now we have the same single power on each side, same base, right? Not multiple of them on each side. Want to get it combined down to 1 on each side. And then once it's 1 on each side, we just can ignore the e. Right? Again, there's math behind to actually making the e go away. But we can say, oh, I can just ignore it. And so that leaves us with 3 plus x equals 5x. And can you imagine me giving you a easier problem to solve than that? I hope not. Okay. So subtracting x from both sides, divided by 4. There's x. So you're not actually just making them go away. Okay. There's no math that just says they go away. Right? You can't divide both sides by e or something like that. That's not how it works. Right? It's going to deal with a logarithm if we actually want to go into it. Okay? But we don't need to. Okay? Any questions there on number 1? Okay. Now looking at number 2. Number 2 is a little trickier because the bases are not the same. Okay? So essentially our job is to make the bases be the same. So we got to figure out how to do that thinking. So we look at our bases and say, I got 27 and I got 9. What do they have in common? That's something we could take advantage of here with 27 and 9. What do they have in common? What about 3, Ruth? You said 3. Okay, so they're both divisible by 3, right? 27 and 9 are both divisible by 3, which is very true. Unfortunately, it's just the wrong type of thinking to be doing here. Okay, these aren't multiplication problems; they're exponent problems. So we need to be thinking about what do they have in common in regards to powers, in regards to exponents. Okay, and so we need to think about how can I write 27 as a power of some number that I don't know yet, to some power. And then I want to write 9 as an exponent of some other number, or that same number, so I'm using expo times, to some different power. How do I write 27 as a power of some other number? Or how do I write 9 as a power of some other number? Colby, could you write 27 or 9 as a power of some other number? Maddie, could you write 27 or 9 as a power of some other number?
Wouldn't 9 be 3 squared and 27 be 3 cubed?
So 9 is 3 squared, right? And then sometimes it's who is that? Is that Victoria? Or Rhea?
That was me.
I don't know, Rhea. There's no me. It doesn't show me like who's talking. Okay. Yeah, right. Sometimes it's easier like just look at one of the numbers. You might confuse yourself looking at both of them. So like you look at yourself, should I focus on 27 or should I focus on 9? Like which number might be more familiar to you, right? And hopefully you look at 9 and say, oh, 9's 3 squared. Like you got to make sure your brain's kind of in the right mode, right? I got to think of it as a power issue, right? Which of those numbers seems to be more familiar power? You should be pretty darn familiar with 9 as a power, or as being 3 squared. And once you kind of have a base to go off of, like 20, can I make 27 out of 3s? Is 27 3 to some number? Like now that you have kind of a starting point, like, okay, can I do it with 3? You might be in a better spot rather than trying to figure out them both at the same time. Does that make sense? You can try to figure out one of them and then see if you can use that base, the 3, to then also do the other one. But trying to do them both at the same time is probably going to be kind of confusing. Okay? And so what we can do, knowing that 27 is 3 cubed, good job, Ray, and 9 is 3 squares, we can take those original numbers out of the problem and replace them with these powers. And so when I do that, right, we're using substitution ideas. So I'm going to take that 27 out. The x is still there. I'm going to take that 9 out. The 3x minus 1 is still there. I'm allowed to replace 27 with something that it's equal to. I can't just replace it with anything. I can't just shove a 9 in there. But 27 is equal to 3 cubed, so I can replace 27 with 3 cubed. right? And 9 doesn't equal 3. I can't just shove a 3 in there, but 9 equals 3 squared. So I'm allowed to replace 9 with 3 squared. Okay? It has to stay equivalent. So I've gotten the problem nicer because now they're both base 3. And eventually I'll be able to ignore the 3's. But before I can ignore the 3's, I've got a little bit of work to do. So what happens on that left side? Caleb, what happens there? Wesley, what happens here? Nope, don't cancel. 3 to the third to the x. What happens with the 3 and the x? Okay, multiply. So we get 3 to the 3x. What happens here? 3 squared to the 3x minus 1. They multiply. Okay, when we do multiplication like this, what do we got to make sure we do though? Two times 3x minus 1. How do we actually do that? Yeah, we distribute, right? It is multiplication, but it's also distribution, right? So we get 3 to the 6x minus 2. Okay? And now that they're both base 3 and they're both as simple as I can make them, now we can ignore the 3's. The 3's aren't canceling, the 3's are not dividing away. And again, the actual math behind getting rid of them involves a logarithm. We're not going to worry about it because we know just a faster way. We can observe patterns and say, oh, I can actually just ignore them. They're not, the 3's don't matter here. So again, we get this down to a really simple equation. Okay. Subtract 3 from both sides, add 2 to both sides. So x equals 2/3. Right? You know, and how do you know if that makes any sense, right? How do you know if that's right? Especially when you get something like 2/3, you can be kind of like, oh, I have no idea if that's right or not. Okay? So you plug it back in. 27 to the 2/3 power is supposed to be equal to 9 to the 3 times 2/3 minus 1 power. So remember when you're checking, you do not solve, you do not move anything across the equal sign. You purely simplify that one side down, you simplify the other side down. Rational exponents mean, 27 to the 2/3 means the cube root of 27 squared. Cube root of 27 is not 3. 3 squared is 9. Nine to the 3 times 2/3 minus 1. 3 times 2/3 is 2. So I'd have 9 to the 2 minus 1. Well, that'd be 9 to the 1 power. Of course, 9 to the 1 power is equal to 9. So we can see that our answer works. 9 equals 9. Okay, so you can always check your answer. Any questions there on 2? So the key to this process is, can you identify a relationship between these numbers? Okay, that's the trick, right? It's not always easy. It's a lot of abstract thinking. There's no way to write this down really to make it easy. Okay, you got to look at the numbers and start just messing around. Okay. Now there's ways to make it easier, perhaps. There's no way, I wouldn't say really any way to make this easy. So I'm going to focus on that 1/4 and the 8. I want to see, how can I write 1/4 as a power of something, and 8 also as the power of that same number but with a different exponent. And again, sometimes it's easier to maybe look at one of the numbers than both of them at the same time. So if you're going to try to figure out one of these numbers as a power, which one maybe would be the easier of the two to look at? Would you rather look at 1/4 and try to figure it out as a power? Or would you rather look at 8 and try to figure it out as a power? Which one would be easier? I agree, Maddie. I think 8's probably an easier number to look at first, right? So how do we write 8 as a power? What's 8 equal to? Some number to some power equals 8. Some number to some power is 8. What number can I raise to a power and get 8 as my answer? There you go, right with 2 to the third. I expect you guys to recognize that. 8 is 2 cubed. You should know what 2 cubed is pretty quickly. Okay? Just like you should know what 3 squared is pretty quickly. Right? And recognize 9 as 3 squared, recognize 8 as 2 cubed. Right? That's the mode your brain should be in right now. You guys aren't going to be doing anything crazy. Okay? I'm not going to be expecting you to recognize that 27 to the 2/3 is 9. Okay? But it should be simple powers, like 2 cubed. Now that we know that our base could be 2, can I write 1/4 as a power of 2 also? Can I use the same base for 1/4? Yeah, 2 to the negative 2. So we gave ourselves a place to start from. And then once we had that place to start from, we'd check to see if we can, continue down that path. Now, what if we'd gone the other way? Right? What if we'd tried to figure out 1/4 first? Probably the easiest thing to think about 1/4 as a power would be 4 to the negative 1. Right? Now, it's not always going to happen this way. But when you go to try the other way and you say, well, what about 8 as a power of 4? Well, there is no power of 4 that's 8. And so there's no simple power of 4 that's 8. And so this one breaks down. Okay. But generally, I would start with the whole numbers first, guys, versus trying to start with the fractions. And hopefully that's kind of makes sense. So we don't have to deal with negative exponents first off. Okay. But you guys are going to have more familiarity with whole numbers rather than fractions. It would make things easier on you. Okay. So there's our connection. There's our common base is going to be 2. So I want to go and replace what I had with what I know now. Okay, so I've taken the 1/4 out. I've taken the 8 out. The exponents need to stay put. 1/4 is equal to 2 to the negative 2. 8 is equal to 2 cubed, so I'm replacing it with something that it's equal to. Okay, I can't just put 2 in there because they're not equal to 2. I have to replace with something that's equal to. And just like before, those are going to multiply. Those are going to multiply. So I get 2 to the negative 6 equals 2 to the 3x. And again, at this point, we can ignore the 2's and say that negative 6 equals 3x. So x must be negative 2. If you're really not sure about that, that works. 1/4 cubed equals 8 to the negative 2. Is that actually true? Well, 1/4 times 1/4 times 1/4 would be 1/64. Then 8 to the negative 2, and the negative makes it a fraction. 8 squared is 64, so we have 1/64. So we can see that it does indeed work. Okay. So there's certainly nothing stopping you guys from checking your answers. Okay. Again, this is an abstract process, trying to figure out those connections. Okay. But make sure you're thinking about in a power way. How can I write 8 as a power of some other number? How can I write 1/4 as a power of some number? I don't want to look at those and go, they're both divisible by 4 or something like that. It's not the thinking I need to be doing. Okay. Anything on 1 through 3 there you guys want to talk about? All right. So what if the bases are different? I'm going to change this real quick. So this step 2 here was the way that I learned how to do logarithms. I don't like that way anymore. Over the years that I've taught this, I really think this other way that I do is much better. Just because I'm better at everything than anybody else. So what I've been on you guys about, that idea of how do you move between the two forms, and what we were doing on Thursday. It says this, let's rewrite it as this. Okay? I really think this is a much simpler way to solve these problems. The first step here being isolate the exponential expression, and what that means is that this piece here, we're not going to do number 2 right now. We may come back to that later, but we're not going to do it right now. That piece right there needs to be isolated, so that if this problem said like 4 to the x plus 10 equals 25, my first step would be to subtract 10 from both sides. If this problem said 2 times 4 to the x equals 30, my first step would be divide by 2. Okay, so we want to isolate that power first. So we can see on number 1 that the power is already isolated, so we don't need to worry about that. Okay. Step 2, we're going to rewrite it as a log, and that's what we've been working on so often, for so long here. So the base of our power is 4, so that means that's going to be the base of our logarithm. So log base 4, and then remember the x and the 15 are going to switch spots. So log base 4 of the 15 is going to come over, and then the x will kick to the other side. The exponent will be the other side. So log base 4 of 15 equals x. Think about our goal here. Our goal was to solve for x, and so that's what we've done. X is by itself. X has been solved for. We may not know what it's equal to, because I don't know what log base 4 of 15 is, but I know that it's equal to x. Okay, so I do know what x is. I just don't have a nice number to attach to it. Okay, so how do I figure that out? How do we figure out what log base 4 of 15 is? How do we figure out what log base 4 of 15 is? Change of base. What would that look like, Maddie?
Wouldn't it be log 15 over log 4? And you just put that into the calculator?
If you said more, I didn't hear you.
Log 15 over log 4.
Log 15 over log 4? Or natural log of 15 over natural log of 4. It does not matter which one you pick. You just need to be consistent. You can't mix them. Okay, that's the change of base, and I know some of you guys have calculators that'll do that, but this is the expectation, is that you guys will know how to do it by hand. No, we don't all have calculators that can do it. So the change of base property, or the change of base formula, whatever you want to call it, okay, expect you guys to know how to do that. And so there is our exact answer. So you'll notice that the problem says, express the answer in exact and approximate form. So this is our exact answer here, whichever one you choose to write. And then we're also going to go ahead and say, well, what is that approximately? So some of the problems will have exact answers and approximate answers. Some of the problems will just have exact answers, like we got 2/3 or 3/4 before. That was it. Okay, but now we need to go in the calculator and say, what is this actually equal to? So, function, I'm just going to pick natural log because it's at the top, divided by function natural log 4, right? So 1.953 with, let's go ahead and go to the third place, the thousandth, 1.953. Okay. We are going to skip this for right now. Just talking to, because there's a variable on both sides like that, and because the bases are so different, this is actually pretty, like that's about as complicated of an exponential equation as we could solve. I'm not sure if I want to do that with you guys or not. I was talking to Ms. Harris about that. She said that is something that's on the like the KU final, so she was going to make sure get that down with her students. No, I wasn't necessarily too concerned about doing it right now, but we may come back and like just glance at it tomorrow just to talk about it. But I wasn't thinking I was going to push you guys that far for this class. All right, so moving on to question 3. So we need to isolate that power. So Tiger, what should we do first to isolate the e to the 3x? Tiger, what should we do first to isolate the e to the 3x?
Divide by 1.2.
Try again. What can you do instead, Tiger?
I'm not sure, sorry.
What else needs to change? What else on that side of the equal sign would we need to deal with?
The 0.3?
How would we get rid of that?
You just add it to both sides.
Okay. And when we're solving, are we supposed to do addition, subtraction stuff first, or are we supposed to do division, multiplication stuff first?
Addition, subtraction.
Okay, so first step.
So add 0.3 to both sides.
There you go.
And then you divide by 1.2.
There you go.
Okay.
So that gives me 0.9. Divide by 1.2. Divide by 1.2. So e to the 3x equals, now 0.9 divided by 1.2 is the exact same thing as 9 divided by 12. If we just move the decimal place once on each one, right? Since I'm doing the same thing to both, it's okay. I'm not changing anything. Just changing the way it looks. And so 9 divided by 12, or 9 over 12, what's 9 over 12 reduced to? Try again, Ruth. There you go. Okay, that's perfectly okay to do, right? Just recognizing that they're both one decimal. I can move that decimal, right? I mean, chances are you wouldn't recognize this 0.9 divided by 1.2 as being 3/4, but it is. Okay, so just changing it just slightly makes it so much easier. All right, so our power is isolated. E to the 3x equals 3/4. So here's that key step, right? What do we need to recognize about our power that's going to affect our logarithm? What do we need to recognize about that power that's going to affect the logarithm? Victoria, what's important about this? Katie, what's important about this? Nope, not the x. What do I need to be kind of keen on as I go into that rewriting this as a logarithm stage? Yeah, okay, it's the natural log, right? Okay, since it's base e, it's going to be a natural log. So the natural log of 3/4 equals 3x. Okay, so e drops down, the 3/4 and the 3x switch places. Okay, so we have the natural log of 3/4 equals 3x. Now notice that x is not completely solved for, but we have eliminated the biggest issue with x is that it was up in the exponent spot. So we brought it down to the normal level of the equation. but it's still not alone, okay? And again, the natural log of 3/4 is some number, just like if it said the square root of 3/4. It's just a number I don't want to deal with because it's going to be a really gross number, okay? So we don't want to put that in our calculator right now. It's a bad idea. So what we want to do is instead just keep solving for x. So I'm going to go ahead and divide by 3, okay? So x equals the natural log of 3/4 divided by 3. There's my exact answer. Then we'll go to the calculator to get the approximate answer now. Do not round during the middle of a problem. It would be inappropriate to type this in, round it, and then divide it by 3. Okay. Now that I'm done, I can start rounding. So function, natural log, 3 divided by 4. Make sure you get outside of your parentheses to get the divided by 3. Okay. Then you go over and you look at the left side, make sure it's typing appropriately. Does that look like what I wrote? Right? Natural log of 3/4 divided by 3, make sure they match. And then we get negative 0.096. Negative 0.096. So exact answer, approximate answer. You guys need to be prepared to have both. Anything out of these 5 you guys want to talk about? No, Mr. Baker, you did a wonderful job explaining it all. It was very clear. Thank you. I appreciate that. Okay. So the other side of this is the logarithmic equations. And so we're seeing that there's 2 different types here as well, made up of problems that have logs and a constant. So here we're seeing 2 logs and 1 constant. Here we're seeing 2 constants and 1 log. Okay, so some sort of combination of logs and constants versus problems that just have logs in them. So log, only logs. Okay. You will notice that on all the problems with multiple logs, then they all just have one base. So log base 6, log base 6, log base 2, log base 2, log base 2, log base 5, log base 5, log base 5. Only log there is log base 8. Okay. If the problems had different log bases, the problems would be much more difficult. Okay. So not something that we're going to get into. And we're also not going to get into this. You'll notice that as far as the 2 ideas go about solving here, they actually start off saying pretty much the same thing. Use log properties to express as a single logarithm. So we're going to be taking these logs and combining them. Or we have a different word for that, condensing them. So if you have multiple logs on one side, you want to get them to be 1 log. Okay? Or you want all the logs to be on one side and then the constant to be on the other. Okay? We want just 1 log in the problem, not multiple logs, or we want 1 log on each side, okay, without anything else. So both of these essentially come down to that idea of condensing the problem. Which is something we talked about the other day. We talked about it when we were looking at page 97. That's where your properties are. In your notes, okay? So you might need to flip back there and look at those real quick because that's about what we're about to start into is how do we use those log properties to condense the problems. That day we learned those, we talked about expanding them, pulling them apart, and then pushing them back together. And I told you when we would use the condensing to help us solve. Here we are trying to solve, here we are trying to use the condensing to do that, okay? So if you need to glance back at page 97 to look at your log properties, do so now. And my question is going to come down to, where did addition come from? Where did this addition come from? Victoria, what do you think? Where did that addition come from? What log property? What do we use?
Is it the product rule?
Okay. So what's that mean it came from then? The addition came from what?
Multiplication.
Multiplication, right? So that means we need to take those arguments and we need to multiply them. Now they're both log base 6. So our new log is also going to be log base 6. And of course, 2 times x plus 2 is 2x plus 4. Okay? This is where we need the problem to be. So there's one log on one side, and then a constant on the other side, or one log on one side, and then one log on the other side, and that's it. And then this comes down to, what is a log? Right? So I've been talking to you guys about is, use your thumb or whatever, cover up that right side, and you look at log base 6 of 2x plus 4. Piper, what does log base 6 of 2x plus 4 mean? What does log base 6 of 2x plus 4 mean? Nope, not 6 to the power of 2x plus 4. What's log base 2 of 10 mean, Andrew? Log base 2 of 10. I couldn't hear you, sorry. It's very choppy.
Oh, wait. 2 to what power equals 10? So,
Okay, good.
oh, I just mistyped.
Okay, what do you mean to say?
6 to what power equals 2x plus 4?
All right, 6 to some power equals 2x plus 4. Right, but we actually know the answer. It's not 6 to what power equals 2x plus 4. It's 6 to the second power equals 2x plus 4, right? And so what's the question? Oh, and we also know the answer. Right, but I really want you guys to make sure you're focusing on the question. 6 to what is 2x plus 4? Oh, 6 to the second is 2x plus 4. So what we've been able to do there, guys, by rewriting it as an exponential equation is unlog the problem, right? Notice how the x was stuck inside of the log. Remember, a log is something you're doing to a number. Just like if it said the square root of x equals whatever, you got to get rid of that square root. So to get the x out of the square root, we don't divide by a log or something like that, because log's not a number. Log is an operation. It'd be like dividing by subtraction. Doesn't make sense. And you have to unlog it, and the way to unlog it is to rewrite it as an exponential. Okay? Of course, 6 squared is 36. And I subtract 4. And then divide by 2. There's our answer. Okay? But once you get it down to an exponential equation, the rest should be simple. All right, so there's that key step, right? Rewriting. Okay, well, you guys see why I've been on you guys about how do you do that? Be really good about it. Okay. Number 2 here, pretty straightforward. Just got a little bit of isolating that we need to worry about. That this log needs to be isolated, the log on one side and the constant on the other. So our first step here just being to get rid of that 20. Again, with the natural log, we want to make sure we're paying attention because that's base e. So as we go to rewrite it, it's e to the what equals 2x minus 7. Well, it's e to the third equals 2x minus 7. So do that rewriting. Now again, e is a number, 2.72, right? But it's a big long gross number, and if we cube that big long gross number, we're just going to get some other big long gross number back. And we don't want that right now. We just want the simplest thing we can write, the most exact thing we can write. So we're going to leave it as e cubed. We're going to continue to solve for x. Okay? So this idea of exactness, of not introducing rounding into the problem until you absolutely have to, which should always be at the very end. So there's our exact answer. And then we want to type that in the calculator and get our approximate answer. Anything about our exact answer there you guys want to talk about before we go into the calculator? Does that make sense, Ruth? Does that make sense, Grant? So remember, Maddie, natural log of 2x minus 7 is the same thing as log base e of 2x minus 7. When I say log base e of 2x minus 7, I'm asking myself e to the what is 2x minus 7? And if our answer is 3, then that means that e to the third is 2x minus 7. So e to the third, was it plus 7? Yes, plus 7 divided by 2. You look over at the left side. Was that what we'd written out earlier? Nope. So what did I mess up? What do I need to add when I'm doing the calculator work versus when I'm doing the writing work? How do I make the calculator understand what I want? Yep, need parentheses right here. Okay. So we got to make sure your calculator understands that all of this is being divided by 2. So you make sure you group it for the calculator. You don't need to write it, but we need to type it. It's your job to communicate to your calculator correctly. Close those, divide by 2 now. You look over at the left side. Okay, that's what I wrote. Go to the right side, 13.543, 13.543. So we have our exact answer, we have our approximate answer, just like before. And again, you could check that. 20 plus natural log of 2 times 13.543 minus 7 is supposed to be 23. So I can type that in the calculator. I can type that left side into the calculator. 20 plus the natural log of 2 times 13.543 minus 7. Those are my parentheses, enter. Right? Really close to 23. Okay. See how our answer works. Anything there on the type 3 examples you guys want to talk about? Okay. Cool. Thanks, Victoria. Thanks, Ruth. All right, type 4. So we have logs on both sides, which is fine, but we don't want multiple logs on the same side, so we're going to condense those. Okay. So if addition came from multiplication, then subtraction comes from raise your hand. So we're going to take log base 2. It always just gives you the same log base back of 5x over x plus 2 equals log base 2 of 3. I can always put parentheses around those. now that they're both log base 2, just like before with if they're both 2 to the whatever, we get to ignore the log base 2. Again, there's math behind making the log actually go away, which is going to be going exponential. But we can just think about a different way. We can say we just ignore the log base 2s and focus on what's inside the parentheses there and say, okay, well, that means that 5x divided by x plus 2 must equal 3. Okay. So if I want to solve for x here, first thing I need to do is multiply both sides by x plus 2. So that means 5x equals 3x plus 6. Make sure you distribute there. And subtract 2x's, or subtract 3x's, gives you 2x's. And divide by 2, you get 3. Okay. Now we do need to be careful here because of the division we did. Okay. We're not allowed to divide by 0. So if our x value made the denominator 0, we'd be in trouble. Okay. Well, plugging in 3 does not make this 0, so we're okay. The other thing we can't do with logs is we can't take a log of a negative. So if our x value made these negative or 0, anything less than 1, not less than 1, anything 0 or less, so anything equal to or less than 0, we'd be in trouble. So plugging 3 here does not make that 0, less than 0 or 0. Plugging 3 in here does not make that 0 or less than 0. So we're okay. All right. So watching this idea of the domain, all right, that the argument can't be less negative, the argument can't be 0. Okay, so any of those things happening would mean our answer would not work. Okay. Last one here, I know we're short on time, but it should be pretty fast. So log base 5 of x plus 3 plus log base 5 of x, those are going to multiply. So I get log base 5 of, that'd be x squared plus 3x equals log base 5 of 4. Since both sides are log base 5, I can ignore that. So I get x squared plus 3x equals 4. Since this is a quadratic equation, just like we mentioned earlier, we want to solve using factoring in this case, since this one's going to be easy. So I'm going to kick the 4 over, make one side 0, try AC method. My AC is -4. I need factors of -4 that add to be 3, which would be 4 and -1. So it's to be x plus 4 times x minus 1 equals 0. Easy peasy factoring. It means x is equal to -4, x is equal to 1. If we try to plug -4 in, I'd give me log base 5 of -4 plus 3, which would be log base 5 of -1. That's not okay. This one would also give me log base 5 of -4. I can't do that. Okay, you get an extraneous answer there. Plugging it in does not work. Okay, this one will work. I'm not gonna. That would give me log base 5 of 4 plus log base 5 of 1 equals log base 5 of 4. Remember, log base 5 of 1, 5 to the what power is 1, would be equal to 0. So log base 5 of 4 plus 0 would equal log base 5 of 4. So it does work. Okay, so you gotta watch out for these log ones because they do have specific domains that can be used. Whereas when you're solving the exponential equations, those had domains of all real numbers, so you don't have to worry about that. All right. Again, I'll get the assignment made during 7th hour. If I didn't say that to you guys already, I meant to. I didn't have time last night to make it, so I'll do it during 7th hour and get that to you guys. Sorry if that throws off any of your plans. Otherwise, I'll see you guys tomorrow. I'll have time to answer questions just like always. Appreciate hearing from you today.